Hello, hello, everybody. Welcome to another episode of the AI Rebels podcast. We're very excited to have Mike Frank on with us here, who's working with a company called Vaire right now. As a quick intro, Mike is very, very smart. He has a bachelor's, let's see, bachelor's from Stanford, master's from MIT, PhD from MIT, mostly focused on AI and something called reversible computing that we'll be talking about later on in this episode. And we're very excited to have his views. He's worked for, he's done short stints with Microsoft, IBM, worked in Silicon Valley during the dot-com boom. I had to pull up the title here. He was the senior R&D scientist engineer of non-conventional computing and cognitive and emerging computing in the Center for Computing Research at Sandia National Labs. And he just recently joined Vaire, which I think is a big deal. You were at Sandia. Am I saying that right, Mike? Sandia?
Yeah, that's fine.
Okay. You were at Sandia for a long time, so I'm curious, what was it that made you change?
Well, I think it's the right time. And by the way, thank you guys for inviting me on this podcast.
Of course.
It's a
Thank you
great
for joining
venue.
us.
Yeah. And so, my perspective on the industry is that we're quickly approaching limits to the energy efficiency of conventional technologies. And so alternatives are needed. And my interest in reversible computing has always stemmed from the fact that it provides a way to extend the life of digital computing beyond the end of what conventional non-reversible computing techniques can do, at least in theory, right? We still have to demonstrate the practicality of it. But the problem is that if we wait until conventional compute completely hits a wall, we're not going to have solutions ready in time to sort of keep up the momentum in terms of progress in industry at that point. And so we really need to start now on seriously developing these new technologies. My research program had been getting support, from government programs, including at the Department of Energy and other places. But I felt like there wasn't going to be the opportunity within government to grow my program as quickly as would be needed, that we really are going to need massive growth in R&D in this area, because developing new fundamental hardware technologies is obviously a heavy lift. It's it's going to take tens, hundreds of millions, even billions over the long term to fully flesh out a whole new paradigm for computing and get it into place so that it can become the foundation of at least digital compute moving forwards. So I really just didn't see a possibility of executing that kind of growth with just government grants. They're just not set up to support that sort of thing. So it felt like the right time to try to take this into the private sector and to try to raise VC funding and funding from other sources to really intensify the level of R&D in this area. And Vaire has some funding already, and they're actively seeking more. So seemed like the right time. Their vision, Vaire Computing's vision, is aligned with mine very closely, and so it seemed like the right time to make a change.
And just briefly, for those who are perhaps unaware, what is a brief description of reversible computing?
Sure.
Like a high level.
So, right. I'll give a, sort of brief high level description, and probably there are some caveats to this. I'll simplify it for this discussion, but essentially, we have an issue in conventional digital computing that whenever you discard information, so either by erasing it or just overwriting it with new data, you're essentially throwing away the signal energy that's associated with storing that information. So in conventional CMOS, that energy takes the form of electrostatic energy on the capacitances in a circuit node, electrical node in the circuit. And the usual approach is you just tie a circuit node to ground or to VDD reference and just let whatever energy is there bleed away and replace the old data with new data. That's inherently very wasteful. That's like the least efficient thing you could possibly do with your signal energies. It's just throw them away every single time you want to change a bit or erase a bit. And conventional logic does this all the time. Like on every clock cycle, every single logic gate in the active parts of your circuit is replacing old data with new data on its output on every clock cycle, right? Potentially, at least if the bit is changing, it's overwriting the old value with the new value. So it's essentially 0% efficient if you look at how that energy is, how much of that energy gets recovered and reused. So essentially none of it gets reused. Every bit is generated once. When we're done with it, we just throw the energy away. So reversible computing is about doing better than that, better than 0% efficient, right? So what we want to do is recover signal energies, and they can be recovered electrically and reuse them for other operations, right? So your signal energies, it's not the case that you can only use them once and only once. You can, when you're done with a bit, you can do what I call decomputation of the bit value. And in the process of decomputing the bit, you can recover the stored energy and move it elsewhere and then reuse it for other steps in the computation.
It's kind of like really low level caching, to use a very crude analogy.
Yeah. Well, I mean, the point of caching is to bring information closer so that it's more accessible. Yeah. You can access it more quickly and with less energy dissipation. But here, you can think of it as how to efficiently deconstruct information. Normally, we just, like I was saying, we just overwrite information when it's no longer needed. But that's not the most efficient thing you can do. You can decompute it, recover the energy, then reuse energy for new computational steps.
Got it.
And in the long run, this is really the only way to get the energy efficiency of digital far beyond the limits of conventional CMOS when it reaches its limits, which is not very far away. And I think it's also we're not very far from the limits for any other competing non-reversible digital technology. You might do better for some things with various analog types of computing. Quantum computing has things that it's good at, right? But those don't cover all applications that we want to use digital computing for. And so if we really want to be able to continue improving energy efficiency of compute almost without limit, at least we don't know what the limits are for reversible techniques, then you have to do it on the reversible computing path. And so I view it as a new path forwards for compute. You could think of it as a new Moore's law in some sense, but it's on a different trajectory from conventional compute.
Yeah.
The designs of the devices and circuits are different.
Okay. Yeah. That's kind of what I was going to ask is, where are you and Vaire at in this pursuit right now?
Yeah. So, Vaire has a fair bit of IP that they're developing. We had some IP at Sandia. We had a couple of patents there that were developed in my research group while I was there, which includes one that's very important for making this stuff practical for high performance compute, which is a concept for a resonant oscillator, which is sort of a key piece for recovering energy from the circuits. You can reduce the amount of energy that's dissipated in the logic by doing what we call adiabatic switching. But then you still have to do something with the energy that's recovered. And the point of the resonator is to keep that energy in an active form and avoid dissipating it and recirculate it from cycle to cycle. So we had a resonator design that looks like it's pretty efficient, but it needs to be developed in much more detail. And Vaire has other resonator design concepts that they're developing. There's also work being done on the logic side to design efficient logic circuits in the adiabatic reversible style for important applications, including things relevant to AI. So
the idea is that essentially reversible computing can be the platform for, hypothetically, I could be running Mac OS on reversible computers in 15 years.
Right. Oh yeah, anything, right? So since it supports digital, you can do anything with it that you can do with conventional compute. And it's just a question of how much reversibility is in the implementation in your microarchitecture. And, the very first useful chips are not going to be fully reversible. They'll be reversible at the low level inside functional units like individual adders and multipliers, and then gradually working our way up to larger and larger functional units. But the more thoroughly reversible the processor architecture is, the larger the potential energy savings can get. But you don't have to, go all out from the start, and it doesn't make sense to do that. It makes sense to do this incrementally, gradually pushing to.
Yeah. What? And maybe the answer is it's still pending and you're not sure, which is fine. But is there any idea what percent or amount is recoverable in like the decomputation process and then capturing that? Because I'm sure obviously some is lost along the way. Like what does that look like?
Yeah. Well, the general answer is it depends, right? There's a number of factors that affect the energy savings. There's the speed of the low-level devices. What we call the RC time constant of the circuit is important. It determines what's called the energy delay product of these circuits. So if you take the amount of energy that's dissipated in a transition and the amount of time it takes to do the transition to change the value of a logic bit, for example, the product of those is relatively constant. It's determined by what's called the CV squared energy, which is the electrical energy stored on the circuit node. The product of that times the RC time constant. There's certainly an advantage to further scaling, which is what industry is pushing on, trying to make the circuits as small as possible and the transistors as small as possible, because that reduces the overhead in terms of parasitic capacitances, right? So as that stuff gets better, it helps reversible computing too. But another limit on efficiency is what's called leakage. And this has to do with the fact that transistors are not perfect switches. When they're off, there's actually still a tiny residual current flow across the device if there's a voltage applied across it. And you want to reduce the leakage as much as possible. And conventional design wants to do this as well, because if you don't minimize leakage, you get a lot of standby power consumption. There's just a lot of power dissipation, even in circuits that are not active, just from the leakage. And you want to keep that from getting out of control. So conventional process development already works to minimize leakage as well. But, for reversible computing, the energy efficiency is ultimately limited by leakage. And so it becomes even more important to minimize that. So to keep decreasing the energy, you have to make sure the leakage isn't too large. And then the resonant circuits that recirculate the energy, they have a characteristic called a quality factor. And that essentially determines, for an oscillator in general, the quality factor essentially tells you how many cycles it can oscillate for before running down. Like if you consider, a tuning fork or, the spring on the back of a door, it'll, vibrate damp out. And so the larger the Q factor, the more energy efficient each oscillation is, the more of the energy of the system is conserved and can be reused. And so you want the high quality factors as well. So all these things play into what's the maximum energy savings you can get. And the degree of reversibility of the architecture also affects this. So if you're throwing away, 1 out of 100 bits, then your energy savings, isn't going to be more than 99%, basically. But the short answer is, you can potentially improve energy efficiency by orders of magnitude. And how many orders of magnitude is really just a function of how far you want to push it, how aggressively you want to push it, how much R&D development is going into high Q resonators, low leakage switches, re-architecting the design to be as reversible as possible. And there's just lots of details to get right. And so, some pretty serious engineering know-how and just intellectual labor has to go into working out all those details. But we don't know of a specific limit yet to how far it can be pushed. That is a limit that's independent of all of these factors, right? So, I don't know if that answers your question, but yeah.
And do you guys have yet like a kind of like a target savings for your first chip, or is that just way too far out still to have any idea?
It's a little ways out. The first chip is basically just testing functionality of some key components. It's like a demonstration chip to just show investors that this path can work. Because historically, there's been a lot of skepticism about reversible computing. There's a lot of misunderstandings about what it is and what we're trying to do and what the real physical limits are. Because of those misconceptions, there's been, I think, a reluctance in the industry and even, in some quarters of academia to investigate this. Most of the work has been in academia. We've heard rumors there's been some work in industry, but not a lot from what I know. I think it will help to dispel some of the misconceptions. Just have a demo chip that works in the way that we describe, and then after that, we'll be trying to push the efficiency upwards. And each step is not going to be easy, right? It's going to take. It's not a trivial matter, right? It's going to take massive investments to keep pushing the boundaries. Just like it took massive investments to get conventional CMOS technology to the point it is now. And the problem is that CMOS is approaching fundamental physical limits, which means that no matter how much you invest in the conventional path, you're getting diminishing returns and it's going to plateau. So that's a problem, right? So, if there's a new path that at least gets you a return on investment on R&D work that you put in, then, that's valuable, right? So that's what we're trying to provide, an alternative scaling path where we can show there is a way forwards, and it's relatively straightforward in terms of the fundamental principles. But, it's just going to take some hardcore engineering development work to flesh out all the details. Yeah.
So
the
recently
fundamentals are sound. Yeah. Go ahead.
Sorry, I didn't mean to interrupt. Recently,
I was just saying the fundamentals are sound. Yeah. Sorry.
Oh yeah. So recently, I've been seeing a lot about, and I'm probably about to ask an ignorant question because I'm out of my depth here. But recently, I've been reading and seeing a lot about optical computing as well. would this be a competing paradigm to optical computing, or are they kind of paradigms that are overlapping
Orthogonal.
perhaps in some aspects?
Yeah, and conceivably they're orthogonal. They could be complementary. I mean, there's no fundamental reason you couldn't try to engineer reversible optical or optoelectronic components, although there's been relatively little work on that. So sort of you'd have to start from scratch a lot more than we have to on the all electronic implementations. Optical computing is interesting, I think, in general. It has some issues, and I'm not really an expert on that topic, but my impression has been that there's some issues regarding density and cost efficiency, because even if individual operations are fast and energy efficient, if you can't pack in lots of floating point units on a chip, for example, right, just because the waveguides are too large, then that's a big problem for cost efficiency. And the density of the circuits also affects just how much how much you can pack, how much processing you can pack into a given a given chassis, or a rack in a server rack. So I don't know how viable optical is moving forwards. I mean, certainly there's people working on it, but I would just caution people to pay attention to the cost efficiency issues, because any of these techniques can only be successful commercially if they can compete in terms of both energy efficiency and cost efficiency, and maybe you can trade off one for the other. So high performance computing systems, like in data centers, these big AI supercomputers and so forth, typically they cost more in terms of the energy cost to run them over their useful lifetime than it costs to manufacture and install them. So the energy cost is actually dominant these days, at least by a small factor. So maybe you could get somewhere if you can make a system that's just a little bit more expensive per flop, but a lot more efficient in terms of energy dissipation per flop. So there's some amount of trade-off that could be done there, but you can't just completely ignore cost efficiency, right? Or no one's gonna buy the chips, right?
Yeah, that's a fine line to walk. I mean, there's definitely a demand. I know, especially, I mean, that's what makes it challenging for these solo founders, developers that we've talked to, is the cost of, they can build a tool, but then the cost of running that tool with, AI and having to pay so many different fees and all these different things, a lot because of the energy it takes. I mean, it seems like there's a hole there that needs to be filled. I hope it can be sooner rather than later. It sounds like the biggest hurdle right now is funding. Is that right?
Yeah, pretty much. We could make progress faster, right, if we could hire more people to work on the problems, because there is lots and lots of work to be done. And the good thing is that I think the path forward is relatively straightforward. I mean, we know what are the areas where we need to make progress, and the more that we can just dedicate people to trying to crack the problems in various areas, the more quickly we'll be able to make progress. So I do think there's a lot of opportunity. Just there are some caveats as well. There are overheads to the reversible logic design, in terms of complexity, and so you can only ramp up the complexity or degree of reversibility of your smallest components that you're making reversible relatively slowly, and you have to ramp up the increase in quality factors and so forth more quickly. So but that's doable. There's no fundamental reason why we can't do that. As long as you're saving n times, you're using n times less energy per switching event, and there's m times as many switching events. As long as n is greater than m, then you've got an overall energy efficiency boost, right? And so
Yeah, right.
that's the requirement, that you just scale things up in an intelligent way, without it doesn't make sense to go overboard, making every bit flip in the entire computer system reversible if your resonators are only recovering 95% of the energy on the switching, right? So you have to do the engineering intelligently, obviously, but it's not there's no deal breakers in the path forwards, as far as we know. Yeah. So I think it's exciting. It's just there's a logjam coming up with the end of conventional digital compute. We're approaching thermal noise limits and issues associated with that. So
how far out do you think we are from that?
Well, if you trust the roadmap, at least the International Roadmap for Devices and Systems, which is the main roadmap that stuck around after the end of the ITRS, the International Technology Roadmap for Semiconductors, which ended in 2015. Incidentally, because the industry got so competitive, they didn't want to share all of their plans with each other anymore. So, but there's still a public effort being run by IEEE to do road mapping. But according to the roadmap, things are going to be leveling out around 2030. So, in terms of energy efficiency, now you could continue pushing compute performance up if you're willing to just use more energy. And so there's a lot of work going into developing advanced cooling systems now that can cool chips at a much higher intensity level, right? Like right now, chips are hundreds of watts typically for GPUs, right? And soon, if you want to keep improving the performance, you have to get up into the thousands of watts for one chip, which is crazy. There's no way you could cool that with traditional air cooled or even immersion type methods. And so they're going to have to do forced fluid cooling through microchannels inside the chip and crazy things like that, right? And maybe crazy. They can make some progress doing that, but the problem is you still have to pay for the energy, right? So it doesn't reduce the cost of the power consumption. It maybe just lets you pack things in a little more tightly. So, and there's going to be limits to that as well. So
that makes sense.
Yeah. So there's really a lot of problems moving forward. So we don't do this. Yeah. Go ahead.
So do you believe that this poses a plateau for the performance of AI systems? To shift gears slightly.
Eventually, yeah. I mean, if you don't do reversible computing, or if it doesn't work out for some reason, then you've got a big problem, which is that at least the low-level energy efficiency in terms of individual bit operations, logic operations or bit flips in general. And if the efficiency of that levels out, then what can you do? You can try to improve your architectures, and there's still likely room for improvement in architectures, like we've seen with Grok, the hardware company, the one ending in Q.
Right.
And then there's other specialized AI chips out there. There's this Cerebrus wafer scale engine, which I don't know if you've ever seen that, but it's an impressive chip. It's like this, literally like a square, almost a square foot in size, right? And but it takes 20 kilowatts of power to run the thing. And wow. if you ever look at the exploded diagram of the interior of their chassis, it's like all cooling systems. They've got a massive piece of metal that sits up against the chip that they call the engine block, and they flow fluid through that to cool it. So you have to go to great lengths, right, to keep improving the density of raw performance at the bit flips per square centimeter level.
What,
per second.
Mike, do
Yeah.
you think, so I've seen updates like in the medical industry where they're using AI now to iterate through, for example, batteries. We talked about in season one, this development where they used AI to iterate through over 1 million different combinations to come up with a more efficient battery.
Mm-hmm.
Are you using AI in any capacity as you're developing these tools, or is there a plan to do that?
We're not yet, but it probably will come in at some point. We really need more funding to get to that stage. But right now, we're still at the level of hand design. It takes a while to give these problems to AI because you have to figure out,
Yeah.
what the problem space looks like, how you're going to represent it. You need to collect training data
Mm-hmm.
to train up an ML system. In one of my projects at Sandia, which is not something we're currently doing at Vaire, but might in the future conceivably was a superconducting reversible logic style we were trying to develop. And it was very new, and we were still at the stage of figuring out how to build logic gates with that. And it would be really nice to have a machine learning system that could help us with that could, synthesize a circuit for us to implement a given function. But the problem was that we had so few examples of working circuits that there just wouldn't be enough training data
Mm-hmm.
for an ML algorithm. And you could try to produce training data synthetically by like doing some brute force iteration through circuits.
Yeah, that makes sense.
That takes time to set up as well.
Mhm.
So yeah, we could potentially do a lot with AI assisted design of circuits and both digital and analog parts of our
Mm-hmm.
circuitry. And I was going to say earlier, I mean, for improving overall system efficiency, of course, there's software improvements, and those are still happening as well. We keep seeing in AI specifically, we keep seeing, the performance of smaller models being souped up, to greater and greater
Mhm.
levels. I've heard rumors that GPT-4o Mini is actually an 8B model, but I don't know if that's true. But if that's true, that would be insane, given.
Hey, that's
So
like
we'll
the
see.
one.
Yeah,
Yeah, that's like the one leak from the strawberry account that I
yeah,
kind of
yeah.
believe is that like the current 4.0 is the 70B and then 4.0 mini is the 8B. Um,
It
yeah,
could
That's
be. Yeah,
wild.
yeah. I mean,
if it is true, it's crazy.
Yeah.
yeah, the last week has been kind of crazy. If what that account has been saying is true, then there's going to be some big new releases this week, and already there's apparently a better model up on Perplexity. There was a new GPT-4o model released on August 6th, so just less than a week ago. So we'll see. I mean, people are reporting better performance on some problems, but I don't know how thorough the testing has been, and they haven't publicly announced the new upgrades yet. So we'll
Right.
see. Hopefully there will be some announcements this week. But yeah, anyway,
I'm
the
curious.
software progress will continue probably, but it's going to have limits too. Is all I would
Yeah.
say on that.
Yeah, that makes sense. I'm curious, as we're kind of pivoting more towards AI here, with your role, Mike, both now and in the past,
Mm-hmm.
what are some of the biggest changes AI has made to your work, your workflow, your ideas, just like anything? Because you've
Yeah.
been very much in the research and R&D space and working on these various ideas. How is AI affecting all of this for you?
Yeah, it is. It is affecting it some already. Although we don't have specialized AI tools for what we're doing yet.
Mm-hmm.
Of course, I've played around with the large language models, and they've been helpful for doing early stage exploration of research ideas. So I've used both Claude models as well
Mm-hmm.
to help me with analysis, just sanity check things, or to work through some calculation. The Wolfram plugin on ChatGPT came in handy back when they were pushing the plugins. I used that a few times. So it's been helpful. Yeah, it does speed up the process of doing analytical research, certainly of coding,
Yeah.
can be helpful.
Did the release of GPT, I guess the big one was probably what, GPT-3. Did it catch you off guard with your background and everything? Were you surprised with this
Yeah,
craze of AI, or were you like, this was a long time coming?
yeah. No, I was kind of surprised because I mean, I did my master's on AI, but that was in the early '90s,
Mm-hmm.
and since switching to more double E types of directions and physics of computing, I hadn't really been following AI super closely. I mean, I would see things that were in the news, but I wasn't keeping tabs on the progress day to day. And then in I think it was August 2020, a friend of mine said, "Hey, have you looked at GPT-3 yet?" And I hadn't really, and I just thought, oh, that's a terrible name, but he pointed me at some posts by Gwern and some other things by GPT-3.
Yeah.
There was an interesting post on Twitter where someone had asked it to respond to philosophers' comments about itself, and
Interesting.
it said some very interesting things that seemed to have a degree of self-awareness and insight that I thought was quite compelling. And so yeah, I was very surprised at how far things had gotten, and so I started getting sucked into it and playing around with different models on AI Dungeon and interacting with them. And so I thought it was quite fascinating. So I've been following AI closely since then, and developments in the field. So yeah, no, it really rekindled my early interest in AI, because when I was a kid, I wanted to build AI. That was my dream. I wanted to like make robot friends and things like this. So pretty
Yeah.
nerdy, I know. And I actually wrote a little chatbot program on my Radio Shack computer that was sort
That's
of a
awesome.
statistical n-gram based, little chatbot.
Okay.
And it was fun. And I had I had a voice synthesis cartridge. How instead of disk, you would just plug in a cartridge into
Yeah.
your system with some of those early systems. And so I had it talking to me and stuff. But
Oh my
um,
gosh.
yeah, so that was fun. But I mean, it was just a toy back then. It didn't have any real intelligence to speak of course. And then in my master's work at MIT, I was studying decision theoretic methods for AI, like, could you build AI using Bayesian probability and decision theory and all of this stuff, and how would that work? And my conclusion from my studies during that period, that was the early '90s, was that number one, it's sort of fundamentally intractable to do decision theory in any kind of long-term way. Like obviously there's an exponential, combinatorial explosion of complexity, right? As you try to look farther ahead and there's more possibilities. So that's one problem, and which we tried to address by, searching through search trees at a more abstract level. But, no matter what, that there is a fundamental problem of limited rationality and meta reasoning, which is that the more computational resources you spend reasoning about something, the less you have to actually execute, right? And the more time you might waste and energy thinking about things. And then even if you try optimizing the amount of computation you spend thinking about things, there's the same problem at another level. Like how many resources do you spend try and optimize the computation yourself. And you find that logically there's an infinite regress, and it's kind of impossible to formally define even what optimal performance would be at reasoning if you take the meta reasoning problem into account. So that was frustrating. And then also, computers were just nowhere near powerful enough in the early 90s to do much high level reasoning solely through search, even if you try to make it a more abstract type of search. Nowadays, the situation is different, both because the computers are more powerful and because you can combine search with these deep neural networks, right, to evaluate the nodes that you get to in a search tree. So that's how, for example, AlphaZero might work, or AlphaFold, or these newer, presumably Q-star is doing some sort of combination of search with neural net reasoning. So I think there's a lot that could be done nowadays, but things seemed kind of slow back then. It didn't seem like there were any big breakthroughs on the horizon. And to be fair, there probably weren't in the early 90s, but not in the very near term. So I switched to studying physical limits of computing because, if the computers are not powerful enough, and that's one of the big problems with AI, well, what's the limit to how powerful computers can possibly become within the laws of physics? And how do we approach those limits? And so I worked for a little while on DNA computing, back when that was, sort of first becoming a popular subject. And then I switched to CMOS-based reversible computing, which seemed more practical. But I first learned about reversible computing in the context of DNA computing. It turned out that our DNA computer had to be reversible because of how the fundamental thermochemistry of DNA interactions works. And so that led me, I had to design reversible Turing machine essentially for our DNA computing project. And so I thought, well, this is cool stuff. It's potentially very energy efficient. So how do we do it in a more practical way? And then I joined Tom Knight's group at MIT, which was designing CMOS-based circuits for reversible computing. And that's how I got into that whole side of things.
Yeah. Seems like it could really enable some long-term development and increase in AI. Sure.
That's what we hope. Yeah. So, the dream, of course, is that, eventually we have computers that are, orders of magnitude more energy efficient than the limits of conventional technology, based on reversible computing. And we could have potentially much more powerful AI systems using that technology. So, if super intelligence is possible, and it seems to be fairly close at this point, it's still going to be important how much power it takes per human equivalent reasoner, right? And if you look at how much power humans consume, one metric is just to look at the power dissipation of the brain, which is like 15 or 20 watts. But of course, the brain can't function outside the body, at least not with current technology. And so the whole body uses more like 100 watts. But, a person isn't going to be productive at intellectual labor if they're just, I don't know, sitting and locked in a box, being fed through a tube, right? So they need a whole lifestyle, houses and cars and, whatever they need to be happy. And then if you add up, if you take total global power consumption and just divide it by the number of humans, that's like the average human share of Earth's total industrial footprint. It's like 10 kilowatts. Okay. So that's a benchmark that's important, I think. So if you can produce AI laborers that really can completely replace human labor, and if they can each run for less than 10 kilowatts per human equivalent entity, then I think that's a good economic case, right, for building more AGI, right? If it's more than 10 kilowatts, then that's a problem, right? It's maybe not economically viable at that point. So we don't exactly have human equivalent AI yet, at least not publicly. I mean, GPTs and so on are certainly smart in certain areas, but not in others. So by the time we have truly human equivalent AI, will it be more efficient than us? I think it can probably beat the 10 kilowatt mark. Whether it can beat the 100-watt mark is more questionable. If you look at the energy efficiency of an H100 just in terms of flops, and compare it to the brain in terms of synapse firings, if we imagine that a synapse firing is something you could roughly approximate with a flop, then we're about a factor of 10 away from biology, but that's not very far. And by the time we get to the end of the CMOS roadmap, we'll probably be about at brain equivalent efficiency. Of course, there's the question of the overall larger architecture of the intelligent system and if it's organized efficiently. Excuse me. But it's certainly conceivable that we could get beyond brain efficiency. And in fact, if you look at the efficiency of reversible computing, we've done simulations that say that we can get the the energy dissipation for one switching event, one bit flip essentially in a computer, using adiabatic techniques down to about 1/14,000th of synapse firing. So if you can simulate the equivalence of a synapse firing with less than 14,000 adiabatic bit flips, then potentially you get more efficient than the brain for that. But there's still a question of designing that whole system, right, and organizing. Lots of work to be done still.
What I really love about this, though, is like it's such a big bet. I love when people are working on really cool big bets.
Yeah.
It's so cool to hear about.
I know. It's like it could revolutionize computing. It would touch battery life. Like it could touch
oh sure
so many different areas
systems.
that and things I'm not even thinking of. Like it'll be
there's
fascinating.
Medical devices, there's sensor networks.
I'm sure Elon will have it in his spaceships when he sends them out, to the universe.
Space is a potential big application area because it's hard to get rid of heat in a spacecraft.
Right.
Radiative cooling isn't very efficient, and
for sure.
And also, they're generally willing to spend a lot on hardware. So if there is some extra cost to the
there you go,
the more efficient hardware, then maybe that's not such a big deal. If,
that's true.
It's more the weight and the power consumption that matters.
Mm-hmm. That's awesome.
So hopefully someday we'll have Elon helping us ship reversible supercomputer components to the South Pole of the Moon, so that they can
we'll definitely
run
have to have you back on the show when that happens.
That'll be exciting.
Talking from the moon.
Yeah, there you go.
There you go.
Yes, excellent.
I'm measuring the efficiency of our underground superconducting supercomputer installations. And,
we'll definitely give you a call then.
Back. That would be fun.
That's awesome.
So, but there's a long way to go still. But it is exciting. I wanted to do something impactful with my life, and when I was coming up, there were already plenty of people doing quantum computing. It was already a highly popular research area to get into, and I was like, they don't really need one more person, and reversible computing may actually be more impactful because basically it can affect all digital computing and not just the problems that have good quantum algorithms, which is a relatively small part of total computing workloads. So anyway,
we're
see.
definitely excited to stay in contact and see where this ship takes you. I hope it keeps moving faster and faster for you.
Me too. Incidentally, we're going to be at the Hot Chips conference, which is one of the major semiconductor industry meetings at Stanford at the end of the month. So I don't know when the podcast will actually be put online, but
yeah,
if
probably
it's before then,
next week
maybe.
or two, most likely. Yeah.
Cool. So yeah, if people are going to Hot Chips and want to talk to us,
Awesome.
let us know.
You have to pop by and say hello for anyone in the area. That's great.
Yeah.
Mike, is there anything coming on the show that you really wanted to touch on, or Spencer, if there's anything you wanted to ask just before we wrap things up? Wanted to make sure we didn't skip anything.
No, I got all of my answers. I wanted to hear a lot about reversible computing. Because like I said, Mike, I've been following you for a while. I think we've followed each other. I don't remember for sure. I don't remember who I follow and don't follow on Twitter. But anyways, been following you for a while.
Well,
and been very interested to hear more.
Yeah.
Yeah, definitely.
So it was really awesome to get you on here.
Yeah, if I generally try to post new research products in my highlights. So if people want to look through my highlights, they might find some interesting papers or.
Yeah, and for our followers, Mike, what's your Twitter handle?
Twitter handle is Mike P. Frank. Also, if you just Google Michael Frank Sandia, my webpage at Sandia is still up. I don't know exactly how long they'll leave it available since I'm no longer technically an employee. I'm sort of on entrepreneurial leave, but I don't know if that guarantees they're going to leave my webpage up.
Right.
So, but it's still there now, so it's a handy resource. There's a lot of links to related work.
Awesome. Yeah, we'll drop links in the bio when we drop the episode. So anyone listening, check it out there.
Cool.
Awesome. Great. Well, thanks for coming on, Mike. We'll stay in contact.
Yeah.
I'll